safe there. Okay? Next, we're not done. We got the second part. You're not off the hook yet. Okay? The second part says, find the x and y components of the force exerted by the wall. And we already did torques, okay, to figure this out. Now we can use forces, okay? So let me zoom in here to help you picture this here. The wall is really doing two things. I'm going to move this guy out of the way here, okay? The wall is pushing to the right in the x direction, and it's pushing upwards in the y direction, okay? If you want to study architecture, by the way, this is usually where people either make it or they don't make it. It's fun designing like a new floor plan or a new kind of building or whatever, but then an architect can't make a building that falls apart there, right? So this is called static forces and torques and equilibrium there. You're trying to balance it all out there. Statics and dynamics. It's usually where people in architecture programs either make it or break it here. So anyway, now we're going to apply Newton's second law. You guys remember Newton's second law? It's a biggie. F equals what? Mass times acceleration. It looks like a very simple equation, but it's really powerful. What's the net force? It's the sum of all the forces in all directions. So we're going to break this up into two directions. We're going to look at the sum of the forces in the x direction, and then the sum of the forces in the y direction. Okay? And here's what's cool. All of the forces add up to 0 in all directions because this thing is not accelerating. It's sitting there. The acceleration is a big fat 0 for this entire system. So what does this mean? It just means all the forces balance out. Let's do the easy one. In the x direction, okay? What are the forces acting in the x direction? Sideways. You have the wall pushing in the x direction. And why isn't this board fly out of the wall? What's pulling it back? You have the rope, right? Pulling back in the x direction. You see that? So in other words, in the x direction, the forces acting in the x direction are the force of the wall in the x direction, right? And then you have the tension in the string pulling back. Or in other words, the force is counteracted. The force of the wall pushing out to the right is counteracted by the string pulling back to the left there, is what I'm trying to get you guys to visualize there. Make sense? That as this thing is pivoting, the wall is trying to push it out, the string is trying to pull it back. Got it? So now this is actually pretty trivial because we know t, the hypotenuse here, this is going to be the adjacent side to the triangle. This is t times the cosine of 60 degrees. So in other words, if you look at the right angle trigonometry, we're pretty much done because all we have to do is instead of taking the sine of the angle, we're going to take the cosine of the angle there. And since we already know t, which is 331.98, we just multiply what we just got. We take what we just had, and we multiply it by the cosine of 60 degrees, right? And we get a tension in the x direction of 165.988. Let's just round that off to 166 newtons. So in the x direction, the wall has to push out 166 newtons to counteract the pull of the cable that's trying to pull it back into the wall. Hang in there. We're almost done. In the y direction, what the heck is going on in the vertical direction? Well, in the vertical direction, the wall is pushing up. Yeah? What else is pushing upwards? The string in the y direction. And that's balancing out the weight of the person who's sitting on the board right here in the downwards direction and then the weight of the board. Okay? So once you picture it, the math is easy. It's just adding up and subtracting. So in the y direction, let's break down the forces there, right? In the upwards direction, we have the force in the y direction, pulling up. We also have tension in the y direction, going upwards, okay? And then we have to subtract from that the weight of the board and the weight of the person. And those forces all balance out. Or in other words, let's see, 600 and 215, that's 815, right? We can do that in our head. The force of the wall in the y direction and the string pulling upwards is equal to 815. And we can find tension in the y direction. That's not too bad because that's just t times the sine of 60 degrees, right? It's the vertical component of force in the upwards direction right here. Whoa, there we go, okay? T times the sine of 60 there. So now we're almost done. It's like a nasty jigsaw puzzle. We're coming right towards the end here. So if we get out our calculators, we can solve for the final force in the y direction. We take 815 and we subtract from that the tension in the y direction, which is 331.98 times the sine of 60 degrees. And if all goes well, we can take a deep breath. We're almost done. About 527.49. Let's just round off to 527.5. Force in the y direction is 527.5 newtons. So in a nutshell, what did we just find? We figured out how much is the wall. Okay, let me clean this up a little bit here. Pushing in the x direction and in the y direction.